The working of differential and operational amplifier. Differential amplifier is a key to understand the op amplifier. So it is a differential amplifier. V1 and V2 are the two inputs. There are two input signals applied at here and at here. The differential amplifier will gives us an output V0. V0 proportional to the difference between the two inputs. Mean V0 proportional to V1 minus V2. Now replacing proportional sign by a constant, let that constant is A, and A is called the gain of the differential amplifier. Like the gain A is equals to V0 divided by the difference between the two signals. So this is the output voltage which appears at here because second terminal is grounded. Okay, so this is a circuit diagram for differential amplifier. We are having two transistors Q1 and Q2. This is a emitter terminal of Q1, base of Q1, collector of Q1. Emitter of Q2, base of Q2, collector of Q2. Collector of Q1 and collector of Q2, they are attached together with RC1 resistor and RC2 resistor. VCC supply is given to both the transistors Q1 and Q2. Okay, now that emitter of this transistor is connected with the emitter of the second transistor, and RA is the common emitter resistor to both the emitters of the Q1 and Q2 together. R is the common emitter resistor for both transistors. A minus VEE supply is given at here to this end. Minus VEE is attached to Q1 and Q2. Okay. Now let the input signal, this one is applied at here to the base of Q1. So actually Q1 in this case is serves as common emitter as well as common collector configuration. You know how? If the input signal is given to base, and if the output is taken at here, then this becomes common emitter configuration. And when the output appears at here, common emitter configuration, there is a phase reversal. Like this is, positive going, but output is negative going. This is called phase reversal. This is negative going, and this one is the positive going. Now the Q1 serves as a common collector configuration also, because if input is here, output appears at here, but when the output appears at here with the emitter forward, mean common collector configuration, then whatever the signal, the same will be the signal at here, but slightly the down in amplitude. So the same signal appears at here and is applied to the second transistor Q2. Actually this is N type, okay, that is emitter, and base is grounded and signal is applied. This signal appears where? At the emitter. Base is grounded, then this becomes common base configuration because base is grounded, and signal appears at here. Common base configuration gives us the output same in phase as that is here. Common base configuration gives us output in phase as that of the input signal. Okay, output and input remain in phase, but it is also somewhat amplified also. So whatever the shape, it has positive going. So this is also positive going. This is negative going. This is also negative going. So you note down, if the input signal is applied to the base of Q1, then at here and at here, the output appears, but this output and this output, there is a phase reversal of 180 degree, V out 1 and V out 2. There is 180 degree phase reversal. Let us consider the case number 2. Now the base of Q1 is grounded here, and input signal is applied to the base of Q2. Now Q2 transistor act as common emitter as well as common collector configuration. Common emitter is like that. If here, if the output is taken at this end, then it acts as common emitter configuration because input is applied to the base. And if the output is taken at the emitter terminal and at the emitter, then it becomes the emitter follower, it acts as a common collector configuration. It acts as common collector. Now let this input signal this input signal, this is the input signal which is applied at here. Okay, and because if the output is taken at this end, then it acts as the common emitter configuration and it gives a phase reversal. So here the output appears, but of opposite phase. Like this is positive going, is the output is negative going. So it's a phase reversal. That's the negative going. This one is the positive going. Now on the other hand, the signal which is appearing at here and appearing at here, then it acts as a common collector, and whatever the shape of the signal, the same shape will arrive at here, will appear at here, but slightly down in amplitude, as it is now common collector. It acts as common collector. So same type of signal but slightly down in amplitude. Now it is appearing at the emitter, base is grounded, input signal is at the emitter, then it acts as common base configuration. So this transistor is common base is common, input is the emitter. So output appears at here of the same shape as that of the input. Like the signal at here, the output exactly of the same shape, no change, and also amplified. Now here, so ultimately was the conclusion. At here and at here, the signal appears. This signal is out. This signal, okay, it is in phase with the input signal. This signal which is at here, it is opposite phase. It is of opposite in phase with that of the input signal. Okay, this is our case number 2. Now the conclusion of the differential amplifier is, like, if the input is applied to Q1 and the base of Q2 is grounded, and if the output is taken only at the collector of Q2, then whatever the shape of the signal, the same type of the signal will appear at the output, but in an amplified form, as it is in phase with the input. Okay, this type of input is called non-inverting input, because the same type of signal will appear at the output but in amplified form. Remember, if the output is taken to the second other transistor, input is given to one and output is taken from the second transistor, from the other transistor, not of the same one. Now, but looking at here, if the input is signal to the base of this and base of this is grounded and output is taken to this of the same transistor, output is taken at the collector of the same transistor, then there will be amplified output, but there will be a phase reversal, because as positive coin is a negative coin. So this is a phase reversal if the output is taken from the same transistor. If the output is taken from other transistor, there's an in phase. So this type of input is called the inverting input, because the output gets inverted. Okay. Now let's think about if the input appears at the base of Q1 as well as the base of the Q2, then what will happen? And let the output is taken only at the collector of Q2. Then because of this input, output will be in phase, but because of this input, output here will be the out of phase. So here there will be two signals. Because of this input, it will be the in phase signal. Because of this input, it will be the that out of phase signal. Two signals of opposite phase, they mix together at here, and then at the output will be proportional to the difference between the two signals. If the two signals are exactly same, equal, same phase, the output ideally the output will become 0, as the output is the difference between the two inputs, input 1 and input 2. How it becomes the difference? This input gives in phase, this input gives opposite phase, and at here there will be two signals of opposite phase and becomes the difference of the two signals. Okay, this becomes then the differential amplifier. For differential amplifier, there should be two inputs, at here as well as at here. Okay. Okay. Common mode and the differential mode signals. Now, if we're having the two signals like V1 and V2 exactly equal in amplitude and same in phase, equal amplitude and same phase, amplitudes are equal like shown, and they are also in same phase, both are positive going and simultaneously both are negative going, then they are said to be common mode signals. Okay. Now what we mean by differential mode signals. So one signal is this one, V1, and second one is like this, opposite in phase, but same in amplitude. Amplitude wise they are the same, but they are opposite in phase. Then they are said to be differential mode signals. They are 180 degree out of phase. One positive going, second negative going, V1, V2. They are said to be the differential mode signals, equal in amplitude and differs 180 degree by phase. Okay. This is a differential amplifier. Differential amplifier is made up with two transistors, Q1 and Q2. So therefore, there are two inputs, input 1, input 2, and there will be two outputs, output 1, output 2. Okay. The importance of the differential amplifier lies in the fact that output are proportional to the difference between the two input signals. Okay. Thus, the circuit can be used to amplify the difference between the two input signals, or amplify only one input signal simply by grounding the other input. Okay. Now, what the response of the differential amplifier to the differential inputs? When the differential input is applied, so differential input, like here, the second input is grounded and only first differential input is applied to the input number 1. So there are two outputs, Vout1 and Vout2. Vout1 will always be opposite to the Vin1, but Vout2 will be in phase with the Vin1. Vout2 will always be in phase with Vin1, and Vout1 will always be opposite in phase to the Vin1. So this is case number 1. Let me discuss the case number 2. Okay. Now the first input is grounded, and to the second input the second differential signal is applied. V1 and V2, V1 equals to 0 because it is grounded. Now there are two outputs, Vout1 and Vout2. Vout2 will be always opposite in phase to V input 2. Vout2 will always be opposite in phase to V input number 2, and Vout1 will always be in phase with the input voltage 2. Vout1 always be in phase with the input voltage 2. Okay, this to remember, and I explained already, in a previous lesson. Let me discuss the case number 2. Now both the differential signals are applied at both the inputs, input number 1 and input number 2. Both differential signals are applied to both the inputs. Now the output Vout1 and Vout2. Vout1, because of V input number 1 will be opposite in phase, and here there will be a second signal because of V input number 2, and because of V input number 2 the signal will be in phase. So both they match. There is a matching in both the in the two outputs at output number 1. So the signal they sum up and we have a greater amplitude signal. Similarly, Vout2, because of the second input, it will be of opposite in phase, and here because of V input number 1, there will be another signal here because of the V input number 1, and again there will be a signal, it will be in phase because of V input number 1. So the resultant is of the greater amplitude signals. Okay, you note down here for the when the differential signals are applied to both the inputs. Now we'll get at Vout1 and Vout2 a strengthened. We will get a strengthened signal. Okay. Let me explore the response of differential amplifier towards the common mode signals. Common mode signals, they are the two signals shown here They are same in phase and exactly equal in amplitude. Let only one common mode signal is applied to the input number 1. The second one is grounded. This is V out 1, and here we will get a signal opposite in phase to the V input number 1. And at the V out number 2, we'll get a signal in phase to the V input number 1. So this is in phase to the V input number 1. So there are two signals, V out 1, V out 2, and both are opposite in phase. Okay, that's the case number 1. Right. Now let me consider the case number 2. The input number 1 is grounded and the signal is applied, input signal is applied to the input number 2. The V out 1, and here we will get a signal, same shape, same phase as that of the V input number 2. And V out 2 will get output exactly opposite to the phase of input number 2. Okay, V out 2 opposite in phase to V input number 2, and V out 1 in phase to the V input number 2. V out 1 in phase with the V input number 2, V output 2, it is in opposite phase to the V input number 2. Case number 3. When both the common mode signals are applied to both the inputs, input number 1 and input number 2. V out 1 here will be, it is opposite in phase to the V input number 1, and V out 2 will be in phase to the V input number 1. It is in phase with the V input number 1. Now because of the second input, V input number 2, here V out 1 will be in phase with V input number 2. So it is in phase with V input number 2. Now both the signals at the output number 1, now they cancel each other, the result is 0. Similarly here, because of the second input, it is in phase with the input number 2, but both the signals comes out of phase and they cancel each other. Both the signals, they cancel each other at the output number 2 also. So there is no output exactly. So the result is that when the common mode signals are applied to both the inputs, then the resultant will be 0 at the outputs, output number 1 and output number 2. To both the outputs, there will be no resultant signals. So it is important to note down that common mode signals, they are rejected by the differential amplifier. This action is called common mode rejection, as explained already. Now we discuss the voltage gain of the differential amplifier. There are two gains. There are two gains for differential amplifier: differential mode gain ADM and common mode gain, that is AC. And for the ideally differential amplifier provides very high ADM, differential mode gain, and 0 common mode gain. That's the ideal behavior of the differential amplifier. But practically, however, practically there are both gains. There are the gains, differential mode as well as common mode gain, but the common mode gain is very small, whereas the differential gain is very high. That's a practical behavior. Okay, and ideal behavior, the common mode gain should be 0, but practically there is a small common mode gain. Pattern performance of the differential amplifier is that there should be very high differential mode gain and very small common mode gain. Now we define the common mode rejection ratio. Common mode rejection ratio, this is the ratio of differential mode gain to the common mode gain. So it is ratio of differential mode gain and common mode gain. ADM should be high, ACM should be very low. So that's why the common mode rejection ratio should be very high for a good or better behavior of the differential amplifier. And usually it is expressed in decibels, CMRR, like 20 log to the base 10 ADM upon ACM, and can also be written as 20 log 10 then 20 log to the base 10 CMRR.